Zeiss, please go ahead.
Yes, thanks for the introduction, Omar. This is combined work with Gerion, who you already listened to on Tuesday, Omar, who is the chair, and Mario, who left, but you all know. I also want to quickly emphasize that these papers are now also online on archive, so Gerion's version is to be found under this number, while mine is, and this talk is this. So let's get started. Let's talk about non-local games, specifically free and fixed size non-local games, and we will make sense of what that means right about now. So the setup is the following. We have a referee that has 4 alphabets, namely A1 answers, A2 questions, Q1 and Q2, and there's a rule function that we will later put into matrix form that kind of evaluates the value of the game. And it can be a CHSH rule function, so there's some connection to Bell inequalities, but we won't specify this any further than that. And there's Alice and Bob. I wanted to put like the Disney versions, but I was afraid of the Disney lawyers because it's being streamed. I guess that wasn't an issue for some of you. So before the game starts, the 2 players, Alice and Bob, decide on a strategy. That means they each have a complete set of POVMs to A1 and Q1, namely these are these conditional operators. So when they're given question Q1, they kind of perform this measurement and the output is A1, similar for Bob, but there we have this T-hat system. And they also decide on a shared quantum state. Now, in order for them to be better than classical strategies, the shared state should be entangled. But I want to highlight quickly that we know that in games in general, the maximally entangled state is not the optimal strategy. So you get more non-locality from less entanglement. Now also, there are these 3 regimes one could look at. T1 is where you have classical games, and this is there's a reference you could look at, and I have the reference in the back. Then there's this regime where we kind of consider bounded quantum dimension. There's a lot of work by Miguel and others on this, and also by Haley Yee and Oma and Mario and so on from before. And there is this unbounded version when you go to infinity, which was also considered here in this work by Brandao and Harrow. And they are all different settings and have different challenges. In this talk, we will be focusing on this one in the middle, and it will become a bit more clear why so in the next couple of slides. But for now, that's the setup before we start the game. Then we start the game. Firstly, I want to represent such a situation where, obviously, when they decide on their shared state, it's kind of shared. Each of them get their own part, and then they perform a measurement on it. And this is denoted as such. And we come to this first aspect of the title, namely free game. So the referee chooses the questions that he or she distributes to the players by Q1 here and Q2 here, and it's kind of determined with this probability distribution. This is product. This means free. All the stuff in this work basically also applies to general game, where this is not the case, but this is something that we like to look at and has nice applications. Then they perform their measurements, their conditional measurements, as I said earlier, on their part of the state, and they return the answer to the referee, who then decides, based on the rule function, whether it's a yes or no, whether they answered correctly or not. And you do this for each pairing of answers and questions, and you sum of them, and that's the expectation value of winning the game. And yes, specifically, we want to look at this in an algebraic form. It looks not as nice, but we can still look at it. And we go through it calmly. Namely, we denote the winning probability, maximum winning probability as this W, where we have quantum resources of dimension T, game-specific rule function, game-specific probability distribution. We have this normalization factor. We have this tripartite optimization over the state, the Alice's POVMs, Bob's POVMs. Then we have this trace functional, and you see already here, this looks a bit different to what we had before. We introduce classical registers, A1, Q1, and A2, Q2 to have like a block diagonal structure of the problem, but this is just some nicer way of representing it. And then we have the state and the POVMs, which indeed are states. We want them to be positive and complete. That means that if we trace over A1 or sum over A1, we have the identity, and this is kind of a non-signaling situation. And we have the same for Bob. This normalization, why we chose it as such, will become clearer later on. And the question that we ask is, how well and at what computational cost can we approximate this maximum Willing probability? Now, in general, it's very hard. So even classically, there's this PCP theorem by Aronson and others, which says that it's very hard to approximate. Quantumly, kind of the same story, different difficulties, but the same situation. Now, in this realm where you have like bounded quantum dimension, it's also still very hard, but you, as we discussed in this talk, can actually do some approximation, and you can do it put in polynomial time, as we will see. Okay, so let's give you an overview of what's happening. So we will start with these non-local games, and we first will rephrase them in a nicer version. Namely, we will kind of rephrase them as a constrained bipartite separability problem, and I will make sense of this in the next slide. Then we introduce a Bose-symmetric hierarchy, and this Bose symmetry is a stronger notion than just exchange symmetry. And we provide a constrained Bose-symmetric definity theorem, which kind of provides us with a analytic convergence rate to the original problem. These errors are like logical implications, so these are in fact the same optimization problem, whereas all the solutions here are solutions there, but not conversely, but we can kind of revert back the error by this definity theorem. And then lastly, we provide, again, an equivalent problem that is of polynomial size, and this is like a isomorphism, as we will see. So far, so good. So let's start with rephrasing these non-local games as constrained separability problems. So this is the first step in this overview, and I thought that would be a nice graphic, but maybe it's a bit redundant, but you will see it time and time again, so I'm sorry about that. Again, we have this weird-looking version, which is exactly the same on Bob's part, but now we only optimize over this D and an alpha, and this alpha appears here, and this is a state assemblage. So we kind of do a steering trick, absorbing Alice's POVMs together with part of the state, and kind of do a swap trick to get back like this algebraic structure that we want. But now we have like these adapted constraints. We still have positivity, we still have trace 1, but now this is like the marginal state. So this is also some extra algebraic manipulation that we need in order to like attack it with the framework that we introduce in this next slide. So just to highlight, before in this work by Yi and others, this step wasn't done, and it was a tripartite formulation, and you had to kind of deal with all the difficulties of multipartite entanglement and stuff. Here, this is a much easier formulation. Also, we already get a stronger convergence rate in terms of the shared quantum dimension, which is quite neat. Now, because we want to kind of advertise the tools also in this talk and not focus too much on the local game setting, we introduced this broader class of constrained separability problems, which was originally discussed by Datta et al. In semi-definite programming hierarchies. And we realized, because we have made this steering trick, improving the dependence on the quantum dimension, however, at the cost of having more intricate linear constraints. Now, as CSEP problems, constrained separability problems of the bipartite form, we consider such problems where you have in general a state that we have in this trace functional, where G is like problem specific. Before it was the game rule function and stuff like this, and now it's just any basically Hamiltonian you could think of. We have this separability condition, and importantly, we have for every x in this decomposition, so for the marginal states, with these local constraints, such that under these linear maps, fixed operators W, C, A, L, and this reduced state, and linear map on Bob's system, same fixed operator, other fixed operator, but still a fixed operator, and also this reduced state here on Bob's right side. So you realize Alice's system has like a left and the right part, and Bob's system as well, and we have these fixed point constraints. Now, before, there weren't, these were much simpler. These AR and these BR system were always one-dimensional, and there were no fixed point constraints. So for example, so you could only kind of treat situations where you had linear maps that kind of map these states, these marginals to like a fixed operator, and the same for B, and this is obviously more general. And we hope that you possibly have like problems in mind that you can like write in this form, and then the tools that we give in the next couple of slides kind of are helpful for you as well. I want to mention, I guess you're all familiar with this, separability problems of these forms are very hard. First of all, this is non-linear, so I can't write it as an SDP. And also optimizing linear functionals over this space of separable states is NP hard. There's a nice review and like kind of paper on this by Ioannou. So check that out if you want. So how do we go about this? I mean, it's a pretty standard technique by now. When you have separability problems, you do DPS kind of hierarchies, which are basically understood as such that instead of optimizing over the set of separable state, you relax to an outer set, which is the set of n extensions, which are symmetric states, which reduce to the original state. And you can do this for any n, and you converge to the set of separable states again. Now, we want to talk about a stronger notion of symmetry. So we want to talk about a symmetry that allows us to write a SDP in terms of Bose-symmetric states. What is that? It seems a bit weird at first, but let's make sense of this. Namely, Bose-symmetric states are those states where we have, so this is B1 to N, this is like a tensor product, but it's not an IID state. It's just how we denote the systems. And we have this permutation representation acting on this row, B1 to N, and it's invariant. Now, if you recall, the symmetric case would have like a UT or U dagger on the right-hand side. So it's a bit weird that it's only from the left. And similar, we can look at the stronger notion where we have a side system, a quantum side system A, and we look at this symmetry with respect to the side system, and this implies this, but not conversely. Now, why is it a stronger notion? For example, look at the identity on B1 to N. This is symmetric, but it's not Bose-symmetric. You can also think of it in terms of geometrically, in terms of eigenspaces and eigenvectors, a symmetric operator. The eigenspace is invariant under these permutation operators, whereas Bose-symmetric operators, each eigenvector stays invariant, so it's strictly stronger. Now, when you're in rank 1 in pure states, there's no difference, and keep that in mind because we will use it later. But one could also think of it in terms of the symmetric subspace. So the symmetric subspace is given as these, where the things are basically invariant also from the left. You can also think of them as tensor product n states and so on. And based on the symmetric subspace, Standl, Renner, and others kind of already prescribed this really strong 1.5 Definetti theorem, which uses the symmetric subspace, but there are no constraints. And in this talk, we really focus on the situation when there are constraints, because that makes things very difficult. Now, you can think of these also in terms of operator spaces. So the symmetry and symmetric states live in kind of this space, where if you have this Sn invariance or the group algebra invariance on H and N, you can also think of it as like you have all the maps on H and N, and then you look at the symmetric subspace in terms of the operators. But we are now focusing on this space, the Bose-symmetric operators, which are kind of all the operators that have support and range on the symmetric subspace. Okay, so this is our first kind of result. This is this SDP hierarchy, Bose-symmetric SDP hierarchy for the contained separability problems. And you might have noticed now that where's this game setting, we want to keep things general, not only because of notational reasons, but as I said, we hope that these tools might be valuable also to other problems. So we can write a SDP hierarchy which has this objective function where we optimize over such a state, where we have also this copy system of B. We want this to be a state that is both symmetric with respect to A, and these are the adapted maps to this SDP. And now they might look a bit weird because you have these local maps on Alice, and you have basically whatever you have left over on this right-hand side of Alice's system, and the Bob's system basically stay untouched. You have this fixed point condition, and similar in Bob's case. But here, already note that you kind of also need to first trace out this n system, and similar here. Now, this SDP hierarchy, or in this lemma, we claim, right, that this thing converges to like the original value, which is C sub G. and we can give the rate of convergence, and it kind of converges exactly to that in the limit. Now these expressions might seem a bit weird to you. These are like minimal distortions, which are an artifact of the proof method, which we will see in the slides why they appear. But these can be bounded. But these are just like dependencies on the dimension of the local systems. So no extension kind of enters here. Okay, so this is an approximation hierarchy from the outside to the CSEP problem, as you see down here. Let's do the first step in showing that this is, in fact, an approximation hierarchy from the outside, namely that anything that lives like in the original problem is a solution to the original problem, will be a solution in this new SDP hierarchy. And we want to highlight here a specific difficulty that you don't have when you have constraints, when you have no constraints. Namely, when you have no constraints, you can simply assume that a set of separable states, any separable states you can represent by like the convex mixture of pure product states. This doesn't work anymore if your set of separable states is intersected by these linear constraints. This is just factually not true. So we need something else. And you recall maybe that I said, okay, for rank 1, there's no difference between symmetry and Bose symmetry. So what we do is we do a local purification scheme that kind of provides an embedding of these symmetric states of like a smaller dimension into a larger space where the symmetric subspace is kind of neatly aligned with these constraints. Namely, we get these candidates out of any solution to the original problem, here or this one for the CSEP, where we do this pretty good purification on all the B cuts, and we call it locally because you do it for each tensor and not like overall. And I don't show this here, but you can see in the paper that these candidates are Bose symmetric and they satisfy the linear constraints. So any solution from the original problem will be a solution in this SDP Bose hierarchy, which is nice. Now, how do we go about doing the converse direction? With these symmetry approximation hierarchies, the standard tool are definitive theorems. However, standard definitive theorems have the issue that they kind of work with either measure theory or Cartan algebras on like the symmetric subspace, and there's no way you can enforce that your candidate kind of satisfies these constraints. Luckily, there's been some work on by Brandao and Harrow, and also by Mario and Oma and so on, that kind of help us in tackling these linear constraints. And what we do here is an extension to the Bose symmetric case, also to all these new constraints. So we're kind of tackling now this reverse direction. Okay, we have this Bose symmetric constraint Bose symmetric definitive theorem, and let's go through this step by step. So we have this Bose symmetric state with respect to A, rho A, B, B bar, 1 to n. We have these mappings that we had before, and if we assume these relations, and these are exactly the ones that we enforce in the SDP-N Bose hierarchy, then there exists a probability distribution, and these states on A and on B, B bar, such that we can kind of bound the distance to where this is like the solution, the reduced state from the SDP-N hierarchy solution, and this is like a separable state, so something that potentially lives inside the original problem, or is feasible in the original problem, and this distance is bounded exactly by this term, which is the same as you saw for the convergence rate for the SDP in the previous lemma. Now, again, these are minimal distortions, and now, importantly, and that makes it an actual solution of the original constraint separability problem, the candidate satisfies the constraints for all x. So we kind of, by this definity, make sure that, in fact, we can construct a solution. We know how far it is away from the SDP optimal solution, and it is really a solution of the original problem because it satisfies the constraints. And the way we are doing this is, I just want to quickly highlight this, that because we have this new CSEP, we also have like a new definition for symmetric states, but we want to focus on the Bose one here. The way we're doing this is by basically exploiting a result from classical physics and lifting it to our quantum situation. For that, we need to consider these conditional classical quantum states where we measure out the B system, it's mapped to a classical Z system, and then kind of with outcome Z, and then we trace away the Z system, and this is like the conditional resulting state. And then nicely Brandao and Harrow, based on like relative entropies and so on, derived such an expression. So there is a classical quantum state that lives on A and Zn plus 1, conditioned on measuring out Z1 to M systems, conditioning on the outcomes, and similar on the other side, this product state, where we here have this expectation value, which we can like pull in. And the bound on the right-hand side is just in terms of A, so the local dimension to Alice's system, and we have this factor n, which you can see already, like for n to infinity, this gap becomes smaller and smaller. Now, we don't have classical quantum states, but we have quantum states. So we incur an error from this to here, which is kind of captured by this G, which are these these measurement distortions, when we go from Zm plus 1 to Bb bar m plus 1, and from Zm plus 1 to Bb bar m plus 1 here. So, okay, we are a bit further away, but we can bound this as long as we kind of measure with informationally complete measures. So far, so good. So far, we haven't actually ensured at any stage that the constraints are satisfied. This is just a definity with, for now, a worse bound than this 1.5 definity. Now, as I said earlier, the standard definities have no guarantee that they work in this setting. So let's go to how we actually ensure that the constraints are satisfied. So we have to argue twofolds, namely first on symmetry. Firstly, bososymmetric states are also symmetric and also have symmetric marginals. This means that the maps, kind of the linear maps, inherit the symmetry from the states that they act on, and similar, and in the second kind of argument, the linear maps commute with the measurement. So let's look at an example, but first like recall that in the SDP hierarchy we enforce this thing. And I want you to focus that here we map the left-hand side of Bob's system, the nth Bob system to the CBL system. We trace the nth system away and we get this expression. This is just one of the constraints which I highlight how this kind of works. Now, the symmetry arguments that I mentioned kind of ensure that this map, which now acts on m plus 1 instead of n, acts in the same way as this n map. First, we pull this map through the candidate, which is this conditional state, which is obtained by like measuring out 1 to m system, and then we can kind of get a bound on this on the correlation to this m plus 1 system. This is a normalization factor. We can pull it through because in fact this works only on the m plus 1 system and not on the system that we measure out, so we can just pull it through. And here is the step where we say, okay, this map on this state acts the same way as this map, so we can like kind of plug it in, but obviously we have to like take into account that this is the M system, and then we trace away all the classical systems that we've measured out and condition on the outcomes, and we get exactly the solution that we wanted. And this is basically you can do for all the constraints, and you can ensure that your state, that your candidate state that you obtained by measuring and conditioning satisfies the constraints. And this is I find a very unique information theoretic proof technique for these constraint definity theorems. Now, you can actually also use this to obtain inner bounds by actually factually measuring out your SDP candidates. But please look at the paper for more details on this. Now, why are we doing this? What is so valuable in this Bose one as opposed to the symmetric one? So let's focus on this step, and this step is actually the one that gives us the polynomial time algorithm of approximation. Namely, first of all, we need to make sure, when we have these constraints, that our problem is confined to these symmetric spaces, and we show that for all the constraints that they live in their corresponding corresponding Bose-symmetric operator spaces, where you can see that here this is an n-1 and this is n, but this is just that really your SDP can be restricted to these spaces which are polynomial in size. Now, there's a technical difficulty that you need to tackle if you want to talk about computational algorithms, namely that if you do this just as I said, you're not ensured that the objects are represented in the right basis. So a priori, they are exponentially large. So we kind of need to map it to a symmetry-adapted basis. And so we ask, can we kind of construct such a symmetry-adapted SDP hierarchy to this one? And can we construct it efficiently? And this is what we now will cover. Namely, we use sure-while duality. So this is useful, I guess. So this Bose-symmetric operator space, you can think of it being like one component of the normal H tensor n decomposition, is isomorphic to a full matrix algebra of polynomial size. This looks fancy, but the isomorphism can look even more fancy, but like this. But technically, it's just a change of basis, which first of all preserves semi-definiteness. So this is important for the SDP, but also the SDP value. And we construct it from these semi-standard Young tableaus. And you might be thinking, what the hell is going on? So I will just give you an example. So think of this semi-standard Young tableau, which is like 1, 2, 2, and semi-standard means that it can be non-increasing within the row. And because we're in the symmetric subspace, we only need to look at the column, the row n length tableaus and no more complicated structures. And these corresponding Young symmetrizers are then basically the orbits, the full orbit of like permuting these zeros and ones. And this is basically the adapted, will be the adapted basis, sure basis also. Now the question still is, can we do this transformation efficiently? And the answer is yes, otherwise the result wouldn't have been there. So first of all, Bose-symmetric or symmetric operators for that fact are, in the canonical basis, are extremely redundant in the sense that they have the same entries in a lot of, they just have a lot of the same entries. So you have like a polynomial number of distinct entries, even though this matrix is a priori of exponential size. So basically, we need to efficiently access each unique entry in this matrix in order to extract the information that is required to set up the SDP efficiently. And we do this by basically mapping this problem of finding an efficient representation of these Bose-symmetric orbitals to like a contingency table with fixed margin problems. And these can be solved in poly time. So in short, we kind of need only poly n queries to an oracle, returning the matrix entry, which is unique, and we get a unique list of any Bose-symmetric operator. Now, having this, we can, in the next step, take any Bose-symmetric operator and efficiently short transform it, basically doing this Bose-symmetric orbital averages. And this is, again, a bit more of a complicated lemma, but it's for any semi-standard labelings of this simple one-row Young shape. You have a decomposition of any Bose-symmetric operator, where these are the coefficients that we like kind of determined efficiently in the previous slide. But now we need to like do this transformation, where this is like the computational version of the canonical basis of the Bose-symmetric spaces, and these are encodings of these Young symmetrizers. And this can be computed efficiently, and this kind of works on top of this result by Pollack, which uses a map to dual spaces. But now in our situation, we can actually calculate this because we are only in the symmetric subspace. And we kind of reduce this whole sum here to like this expression where you have binomial coefficients in terms of these semi-standard labelings. And these are Bose orbital class function, which are in fact just these coefficients that we determined earlier. So because we can determine these efficiently, we can determine this efficiently because it's just this expression. Now lastly, with these two kind of tools, we can provide an efficient SDP hierarchy transformation. But I want to highlight here this SDP hierarchy. Before the transformation, you can never construct it at first and then transform it, because that's exponentially large. So we kind of hinted that you can like query poly many times and you kind of get what you need out of this in terms of information. And to efficiently construct this transformed in the right symmetry adapted basis SDP, you kind of show that all the expression in this Bose symmetric hierarchy are in fact efficiently computable by arguing that you can extract for each of the expression the coefficients efficiently. And since you have the coefficients efficiently, you can then do the transformation efficiently with the lemma of the previous slide. And since it's a star isomorphism, so it's something that kind of a change of base it preserves the trace, so the objective values are the same. So this thing will be as far away from the original solution of the constraint separability problem as this problem, so we can like by this both symmetric definity bound. And this, when we go back again to our non-local game setting, yields the following complexity result, that for a two-player free non-local game, as we introduced in the beginning, with A answers and Q question, with quantum a system of size T, there exists a poly in epsilon, this is the approximation error, costly transformation, which is this epsilon can be like obtained for this n, from this n to an SDP which is like of this size, so it's poly, but we consider these fixed, so fixed size games, so we can like efficiently approximate the value of the game up to an additive epsilon error. Now, to like finish up quickly, the two things that are interesting to us is, now that we have this more general framework of constraint separability, are there other problems you would like to tackle with these? Like what would be interesting ones? And more on the mathematical side, there are other versions of Schur-Weil duality, mixed Schur-Weil duality. You have the ones for the Clifford group, you have the ones for the Brouwer group, Brouwer algebra. Are there like similar structures, useful structures as this Bose symmetry in these variants of Schur-Weil duality? And with this, I would like you to thank for listening. Thank you for listening, and I'm done. And this is the references here.
Thank you. Questions for Julius? Yes.
So you have shown that all the coefficients can be efficiently computed. If you really want to implement with the MATLAB codes or Python codes, how hard would it be?
On a computer, you mean?
Yes.
I think that depends on the person that's implementing it. So if I'm doing it, I think it's very hard. But I think there are people that probably can do it easier. I mean, these complexity results, right? Let me stress this as well. If you actually do it in practice, I think for the computational power of the that you need for the SDP hierarchy, I think the symmetrization makes sense. All the steps in the efficient symmetrization you probably can circumvent for like lower levels. If you really want to push it, then you need to do these algorithmic procedures that are like efficient in like the construction and yield the polynomial time algorithm. But in practice, it would be interesting to see at what point you would really want to like efficiently sample and so on access, because you need to really avoid constructing this SDP. But I think for like a lot of the smaller problems, running the SDP itself is still more costly than like setting up this inefficient one and transforming it and so on. It would be interesting to see at what point it will the symmetrization will outperform in terms of like computational powers that you have as a resource.
Okay, thank you.
Thank you for this question.
Right, thanks for the talk. So, so I was curious what happens if you, instead of this 1.5 definity theorem, you use this this version by Renato Renner, this exponential one. Can you generalize any of your explained results?
That's a good question. So this exponential one, the state that is close isn't a separable one, or product one is like close to like it's a weird mixture. That's why it's exponential.
It's almost IID.
Almost IID, exactly. Because the proof techniques in their work are generally based on Cartan algebras and so on. I don't see how you can like adapt the constraints to this setting yet. I think you need to work on this self-decoupling lemma by Brandao and Harrell. That's where I think one needs to go to like adapt it to like broader situations, because that's at the moment where you have just the simplest version of like a classical quantum symmetric state. But it would be very interesting to look at this, certainly.
Thanks a lot.
Thanks for the question.
So if there are no more questions, then let's thank Julius again.
Thank you.